So we are happy to have Ushak Rahman from University of Toronto. He'll be talking about non-standard interactions and tau neutrino detection at DUNE.
Okay. Thank you. So first of all, thank you for inviting me to give this talk. So today I am going to talk about these non-standard interactions and the effect of tau neutrino detection on the non-standard interactions at DUNE. So this is based on this paper that I wrote with my group. So Zane and Zizen were the master student of the group and Will was the PhD student. So my responsibility was to teach them about neutrino physics, about non-standard interaction, about the globes software, running of the globes software, and also to mentoring them through the work and then to write the paper. Will was working independently on the tau neutrino efficiency at DUNE detector. So he helped us fix the efficiency for different energy bins for the work. And Nicolina was our group leader. So she was basically helping us in communicating with each other and making the group intact. And then we published the paper this year. So sorry for the mistake in the date. Okay. So the basic outline of the talk is going to be like this. So first I will introduce neutrino oscillation physics. Then I will give a brief introduction to the DUNE experiment. And then I will talk the importance of new tau detection, tau neutrino detection at the DUNE detector, and different beams used in the DUNE experiment for the tau neutrino detection. And then I will give an introduction to the non-standard neutrino interactions and how the NSI will affect the event rates at DUNE. And then I will give the sensitivities and what nu tau adds to the sensitivity of the non-standard parameters. At the end, I will take a brief detour and talk about how nu tau can be used in testing the unitary property of the third row of the PMNS mixing matrix. And then I will conclude the talk. So the key message from this talk is that among all the non-standard parameters, epsilon mu tau is most sensitive to the tau neutrino detection at DUNE. And if we know the mass hierarchy, then nu tau detection can help determine the phase associated with epsilon mu tau, which we call as phi mu tau. And also nu tau detection will have very limited effect on the determination of the standard neutrino oscillation parameters. Okay, so first, a brief introduction to the neutrino oscillation. So we know that in standard model, there are three neutrino flavors: electron neutrino, muon neutrino, and tau neutrino. They are also called interaction states because they are produced in interaction and we also detect them through interactions. But they are not the mass agent states. The mass agent states are labeled as nu1, nu2, and nu3. And the relationship between the flavor states and the mass agent states can be defined by this relationship, where U is a 3x3 unitary mixing matrix. We call it as PMNS matrix in the name of Pontecarvo, Maki, Nakagawa, and Sakata, people who first theoretically established neutrino oscillation phenomena. So let us assume that at time t equals to 0, an electron neutrino is produced, or an electron neutrino beam is produced. Now this electron neutrino will be a combination of these three mass agent states, nu1, nu2, nu3. Now with time, when the electron neutrino will propagate, these nu1, nu2, nu3 have different energies, and because of that, their propagation in their evolution in time will be different. And because of that mismatch in their evolution in time, some of the nu will convert into nu mu or nu tau, and that is the phenomena which is known as neutrino oscillation. Now, until we do the final measurement of the neutrino beam, we do not know whether the beam is at nu state or nu mu state or nu tau state, because it's a quantum mechanical phenomena. So we cannot deterministically say whether the nu e is converting into nu mu or nu tau, we can give a probability of nu e converting into nu mu and or nu tau, and that is what is known as the neutrino oscillation probability. This mass states is the Hamiltonian in the mass base. Is the Hamiltonian in the mass basis.
So this is which Hamiltonian are you specifically mentioning? This is the.
So the Hamiltonian will be in the mass basis. The Hamiltonian will be a diagonal Hamiltonian with m1 square, m2 square, m3 square, where m1, m2, m3 are the mass eigenvalue of the.
No, I am mentioning the Hamiltonian contains what terms in your. What are the terms in a Hamiltonian that you have?
The mass eigenvalue of the three.
That is when you diagonalize, but you have to diagonalize an operator. So.
Okay. So yeah. So before diagonalizing, the U mixing matrix has this form. So in the interaction basis, if we write the Hamiltonian, it will be U dagger, the mass square matrix U, and there will be a 1/2e term where E is the energy of the neutrino beam. Yeah, and this U will have these elements where this Cij is cos theta ij and Sij are sin theta.
Now, suppose I want to start from standard model, then which part of your Hamiltonian you're looking at?
If we so first of all, this is not inside in the standard model. In the standard model, neutrinos are massless. So this is not the standard model Hamiltonian. This is a minimal extension of standard model where we give neutrino mass by assuming an additional right-handed neutrino component that will take part in the Higgs mechanism.
But when you tell mass eigenbasis, so you have some particular Hamiltonian in mind, right?
Yes. So that Hamiltonian is that U dagger, the mass square Hamiltonian U. So U dagger.
But there you already assume that you know the masses in the diagonal form, and then you get the actual Hamiltonian. But it is not clear from there which terms are contributing to this Hamiltonian, right? Switch gauge interaction terms.
Okay, so this will be mostly the Yuka interaction term, and if we write the neutral current Lagrangian in the flavor basis, then this then we can separate this mass this mass basis Hamiltonian from the flavor basis.
Do you have particular gauge choice in mind? Because as you know, the Hamiltonian is gauge dependent. So which gauge is the best to see all of these things?
That depends on that will depend on the model that we will use, the neutrino mass model that we will use.
But typically, what do you choose?
This is a model independent description of the neutrino oscillation. So I'm not giving any special importance on any of the neutrino mass models. So this Cij is the cos theta ij and Sij is the sin theta ij, where this theta 1 2, theta 1 3, theta 2 3 are known as the mixing angles. So then neutrino oscillation probability will depend on these three mixing angles, theta 1 2, theta 1 3, theta 2.
I have one question. So at this stage, are you assuming whether it's Dirac or Majorana type?
No, I'm not assuming anything. So it's more of a bottom up approach. So in standard model, neutrinos are massless because we have not seen any right-handed neutrino. Goldhaber experiment tells us that neutrinos chirality is left-handed. But in the solar neutrino experiment, in atmospheric neutrino experiment, as well as man-made experiments with man-made neutrino source, we have seen that we can only explain those phenomena, the reduction of the signal in solar neutrino or atmospheric neutrino, or even in the neutrino experiments with man-made source, if we have a neutrino oscillation. And to have neutrino oscillation, we need to have neutrino mass, because if we don't have neutrino mass, and the mass should be non-degenerate also, at least two of them should be non-degenerate, then only we can have the neutrino oscillation phenomena, and that explains the solar neutrino problem or the atmospheric neutrino problem or
Okay, but this one CP violating phase, is that affected by the nature of the neutrino? So
This
would
is-
it be still one for Majorana or Dirac?
This is the Dirac CP phase. In neutrino oscillation, even if there is a Majorana neutrino, that does not change the neutrino oscillation probability.
So if there was more than one CP violating phase, you're saying that will not affect
It will
the
not affect the
oscillation
neutrino
probability.
oscillation probability.
Okay, but if one wants to look at CP violating interactions of neutrino, then that will be a deciding factor.
This is the Dirac CP phase. This is not the this is a
Okay. But if suppose one gets multiple phases and
None of these experiments will be good.
are there any experiments? Are there any experiments which can see these?
neutrinoless double beta
Double
take
beta.
experiments will.
Okay.
That's something which knows the nature of myeloma.
Yeah.
Okay. 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 Thanks.
Actually, see.
Okay.
We talk as a combination of delta CP plus delta 1 myeloma plus
Delta 2 Majorana, yeah. But
Okay.
but neutrino oscillation probability does not get affected by Majorana phase. We observe the Majorana phases inside the mass agents, three in the flavor states and 2 in the mass agent states, and they do not come in the neutrino oscillation probability.
Okay. Thank you.
Right. What is your starting point? So this U enters in the mass matrix looks like what? Nu1, Nu2, Nu3 only, or is it?
Can I get a?
Or do you write it using Majorana states or Dirac states? I guess that's my question.
Okay. So we
Just
start
starting-
with both Majorana phase and Dirac phase, but
No, I'm not asking of phase.
Yeah.
You write with Dirac states or Majorana states for the neutron.
we do in neutrino oscillation probability we do not know whether it is a Dirac state or a Majorana
Yes,
state.
but I'm asking concretely your starting point. How do you? I don't know. You show this U, and maybe it was there in the previous transparency or something. I'm not sure.
This one?
Yeah, wherever you start in some writing some basis and so on, right?
This
I mean,
this new one new.
yeah. What is your starting point for the mass matrix?
The
Yeah, just the mass part.
yeah.
How do you
So
write?
this mass part.
Yeah,
Yeah.
mass matrix for the neutrinos.
Yeah.
No, 1/2 mass part only, right? Only the mass part.
Yeah.
Just
So
the mass, they should have a bilinear, right? So like a electron mass, it's just written as psi bar psi.
okay.
Right? I mean that is
okay.
what I'm like. Do you start in a Majorana neutrino or Dirac neutrino?
You are talking about the Lagrangian part.
Yes.
Yeah. So as I said before, that it can be only Dirac neutrino. It can be a combination of Dirac and Majorana neutrino. We do not know, because in the neutrino oscillation experiment we cannot probe the Majorana nature of the neutrino.
No, for you to get those U and all that, where did you start?
So
What was the starting point?
So in the you can write a minimal extension of the standard model where there is one right-handed component, one right-handed neutrino.
No, I'm not
component.
asking for the UV completion, but your effective. So you just wrote a general U with 3 mixing angles and 1 phase. That's it, right? So it doesn't matter where you start from. Is that the point? That it doesn't matter how your mass matrix looks like?
Yes.
But you will get the same U.
Yes.
So you don't have to commit yourself to any particular mass matrix. Is that what you're saying?
Yeah.
If you have to commit, you have to say which exact starting point.
Yeah.
If you don't have to commit, then it's fine.
Yeah. So I'm saying that I'm saying that as long as there are 3 light neutrinos.
So your Nu1, Nu2, Nu3, are those Majorana states or Dirac states? Or can it be either and all of your formalism looks the same?
Just a minute. Yeah.
Sorry, just answer my question. I think my question is only whether nu1, nu2, nu3. Is that a Majorana state or a Dirac state? Or does it look the same independent of each one?
What I'm trying to say is that if they are Majorana state, we have no option to know whether they are Majorana state.
No, in what you are doing, I'm not asking about experiments and all that. You are starting with some formalism. For you, when you start, you have put down nu1, nu2, nu3. Are you thinking of them as Dirac states or Majorana states?
Okay, so
Or does it not matter?
It does not matter. That's
Okay.
what that's what
Then
I'm
I can
saying.
put either one and I'll be fine.
Yeah.
Okay.
Yeah.
All right. Okay.
It does not matter for me.
Okay.
Yeah.
True also for Majorana neutrinos, will the U be same?
If there is a Majorana neutrino, then if we consider a Majorana neutrino, then in this apart from this delta CP phase, there will be the Majorana phases included in the U. As I
When
said,
you show this U, you are already assuming that you are doing everything in Dirac.
in the Dirac state, I will not state we are assuming in the Dirac state.
No, but when you take this choice of U, you are already assuming that.
I'm saying that. I'm saying that. So if I consider both Dirac and Majorana state, then I will have nu E, nu2, nu3, and some U, which is sorry, nu tau, and some U, and then nu1, nu2, and nu3. Now, what I can do is that I can take out the Majorana phases. There will so I can take out two Majorana phases on the left hand side and one Majorana phase on the right hand side, and I can absorb those Majorana phases in the two Majorana phases in the flavor states and one Majorana phase in the mass state. So if that happens, then my nu E, nu mu, nu tau, and nu1, nu2, nu3, they are not the actual flavor states and mass states. They are the flavor states and mass states with the e to the power minus I delta 1, e to the power minus I delta 2, and nu1, nu2, nu3 with the e to the power I delta 1, delta 2, delta 3. But if I do that, my oscillation probability does not change. Even if I put those delta 1, delta 2, delta 3, 0, then also my oscillation probability does not change. If I put delta 1, delta 2, delta 3 non-zero, my oscillation probability does not change. And then I am left with this U, this PMNS matrix U. So that the
probability may not change, but you have to choose these unitary matrices. The elements of it are your eigenvectors. Those may not be observables, but it depends on your basis choice. Which basis are you looking at, then this specific form comes.
And because he's only going to look at oscillation, he has put it into the nu1, nu2, nu3, and nu3. So, if you were to look at something that like neutrino is double beta, I think that redefinition will show up there. But he's not going to look at that.
Yeah.
He's only going to look at oscillation. So they will never go any better.
Yeah.
Just take this matrix and multiply it by the three-dimensional diagonal matrix, which has elements 1, e to the I delta 1, e to the I delta 2. Then that will give you the Majorana terms as well.
Yes.
Which will never appear to oscillation form.
Yes.
What it's saying in words.
Yeah.
But then that way you can say whatever appears in the Lagrangian of the formula, take those flavor bases, then there will be that addition.
Yes, and also I want to mention that even if I don't consider a Majorana neutrino, if I just consider one right-handed neutrino and give it a Dirac mass by the Yukawa coupling, and we fine-tune the Yukawa coupling constant for neutrino to allow the small neutrino mass, then also this will hold true. So I really don't bother whether it is a Majorana mass or a Dirac mass. What I bother is that if I absorb those in the most general condition, if I absorb those Majorana phases, I am left with this, and I can work with this for my neutrino oscillation physics. Yeah. So
Just one correction. If I just look at it as a 3 by 3 unity matrix, there is a possibility of putting two more phases, right? Is that I could put what we call as a Majorana phases that would be there. It's just that has been
yeah, and that will come in your neutrino-less double beta decay experiment. Yeah.
Thanks.
Yeah. And so what I'm trying to say is that this neutrino oscillation probability depends on these three mixing angles, theta 1 to theta 1 to theta 2 3, and these two independent mass square difference delta 2 1 delta 3 1. This m1 m2 m3 are the mass value for nu1 nu2 nu3, and then one CP violating phase, that is delta CP. Now if we write the neutrino oscillation probability without considering any non-standard interactions, any funny things, then we will see that for neutrino oscillation probability to be non-zero, my mixing angles should be non-zero. So there must be mixing between flavor states and mass states, and also delta 21 and delta 31 need to be non-zero, which means I need to have non-degenerate non-zero mass. So that is the evidence that neutrinos are not massless as predicted by standard model, and that is why neutrino oscillation gives me an window to look into the B1 standard model physics. Okay, so this is the present best fit scenario for the different parameters, oscillation parameters. So this is without Super Kamiokande atmospheric data, and this is with Super Kamiokande atmospheric data. As we can see that, so there are you can see that this L delta M3L square. So this L is 1 for normal ordering, which means delta 31 is positive. That means nu3 is my highest mass eigenstate and nu1 is my lowest mass eigenstate, and L equals to 2 for delta 3 to less than 0, and that means M2 is my M2 is my highest heaviest mass eigenstate, and M3 is my lightest mass eigenstate. And we can see that when we do not consider the atmospheric data from Super Kamiokande, we get the best fit point at inverted ordering, but normal ordering has a delta chi-square of 0.6. And when we consider the atmospheric data from Super Kamiokande, we get the best fit at normal ordering, and inverted ordering has a delta chi-square of 6. So that means we cannot determine the inverted ordering even after the addition of the atmospheric data at 3 sigma level. And also we can see that for theta 2 3, the theta 2 3 at the for normal ordering is less than 45 degree, but at inverted ordering is greater than 45 degree. So we do not know the octant of theta 2 3. When theta 2 3 is less than 45 degree, we call it lower octant, and when it is greater than 45 degree, we call it higher octant. And also delta CP is not precisely determined. So my current unknowns are, and the other parameters theta 1 2, theta 1 3, and delta 2 1 is very well determined from theta 1 2 and delta 2 1 are determined from solar neutrino experiments. And then the magnitude of delta 31 has been measured in experiments like MINOS, and the reactor neutrino experiment measures theta 1 3 very precisely. So the current unknowns are this mass hierarchy. So this mass ordering is also called mass hierarchy, octant of theta 2 3 and delta CP.
Super K and without Super K. If we have the data, we would include it, no? I mean, why present without Super K?
Because normally Super Kamiokande atmospheric data should not have sensitivity to mass ordering. But here we can see that at addition of Super Kamiokande data is increasing the mass ordering scenario, and also I guess this is the choice that made.
Sorry, that I don't understand. So it is not supposed to. Meaning what? But then it does.
Sorry, I was wrong. Atmospheric neutrino data should not have mass ordering sensitivity. It should be able to determine the magnitude of delta 31. And I also think that this is a
Sorry, my question is very naive. We have the data. Why do we want to look at without the data? I mean, it's like,
This
it's a
is
very
the-
naive question.
This is the choice made by the global fit group. So this is how they present the data. This is
Okay.
how they present the data.
But so I should only look at the bottom one.
I normally do that. I
Okay.
normally just look at the bottom in my analysis.
And this delta chi squared, what significance would that correspond to? I mean, is that,
I think for normal ordering, inverted ordering, the degree of freedom is 1 because it's either plus or minus.
so
Right?
at what significance is normal ordering favored?
So this is best fit. So less than 3 sigma. So
Okay.
square root of
So
6.1.
it's pretty good for normal ordering.
No, because it's either plus or minus. It's not that it has a range. Mass ordering does not have a range. It's either plus or minus.
If I ask the question at what significance is normal ordering preferred over inverted ordering, what is your answer?
Square root of 6.1.
That's like 2 point something.
Yeah.
Okay.
So less than 3 sigma.
Okay.
So
Thank you.
that means that we do not have a good hierarchy sensitivity yet from the
Okay.
global fit, because since it's is that either plus or minus, we want to have at least a 5 sigma sensitivity for the mass ordering, but we do not even have a 3 sigma sensitivity.
Take the SK data, then because of other ordering, take the SK data, then you prefer the storage. So actually, depending on the data sets you choose, you prefer normal or inverted.
Yeah, I would make this exercise only if I have some doubt with super K data, right? I mean, one can then entertain a possibility. But still, when I have data, I'm not allowed to remove it, right? I would say super K is actually allowing me to determine the ordering is at some 2.5. No, I mean atmospheric.
These are super atmospheric data.
It's not an option for me, but to remove data is all I'm saying.
Yeah,
Unless I believe it has some problem or something.
I think what they want to show is that the super K data is actually helping me in
Yes,
it. So
that's point I see.
so
Yeah.
so that
Which is how I would interpret this.
Yeah, that is the only reasonable answer I have, because this is a choice made by these groups. Yeah.
Okay.
Yeah.
Thank you.
I think
GB region, yeah.
the cross-section uncertainties are extremely different between the two regions.
Yeah, and it's not easy to add super Kamiokande data with the long baseline data or the solar data, because it falls in the completely
Also, the
different.
atmospheric neutrinos depend a lot more on the nuclear scattering, which is much more unknown.
Yeah.
Whereas the solar data is more like electron scattering, which is better understood.
Yeah.
So I think that is why they have traditionally kept it separate.
There might be some doubt about how people have. But it has all been factored in.
Yeah, but you want to be cautious. I would doubt all of those because the cross sections are taken at leading order, so yeah. Yeah, because it's leading order and no one uses the next to leading order, so then you have a lot of uncertainty in how these things will progress. You want to be cautious, you want to keep them both so you have an idea of how it's moving, right? So
Okay, so now the DUNE experiment. So it's experiment at Fermilab, where the detector mass is 40 kiloton and the baseline length, that is the distance from the source to the detector, is 1300 kilometer, and it's still in the build-up process. So probably they will start taking data from 2030. But yeah, but I don't think there is a certainty for that also, because for past many years they are talking about taking data soon, but now the time limit is 2030. Okay, so the objectives of DUNE are these. So first of all, measuring the neutrino oscillation parameters, the standard 3 parameters. Then the neutrino astronomy with supernova neutrino bursts when it happens next time, and astronomical neutrinos from other sources. And also then search for the beyond standard model physics, which is this talk based on. And we have used the DUNE technical design report for the details of the experiment for this work. And now the tau neutrino. So the tau neutrino detection is important because tau neutrino detection will give us a direct test of the unitary property of the third row of the PMNS matrix. And also it will and by doing so it will shed light on the heavily neutral leptons or the sterile neutrino existence. And also tau neutrino can be used in testing different BSM physics. So because of this unitary test, we can use it for non-unitary mixing hypothesis testing or even the non-standard interaction testing. And
It does better than looking at nu E or nu mu, is it?
no. So the third row of the PMNS matrix.
We would like to know all rows, all columns, right? I mean,
Yeah.
so why is nu tau better than nu E, nu mu?
Because DUNE has a nu mu beam, right? So
Okay.
you look at nu mu nu mu disappearance. So that means you look at the muons at the detector, or nu mu to nu E appearance. So you look at the electron at the detector. So that constants the first two row of the PMNS matrix. But for the third row, you knew the nu mu to nu tau appearance probability.
Yeah, so I would like to do all of them.
So
why do you particularly pick out the nu tau?
Nu tau for the third row, because with nu mu and nu E, you cannot constrain the third row.
Okay, this is for constraining third row. Nu tau does better.
Yeah,
okay.
Yeah. And also there is another thing, that nu tau is the most difficult neutrino flavor to observe. We have only observed 22 nu tau so far in Opera and in Nomad. So yeah, that is for the that is for the third row. I mean to constrain the third row of the PMNS matrix. Yeah.
So then it should depend on the whole matrix rather than only the third row.
Yeah. So when I'm talking about this BSM, this unique opportunity, that I mean this non-unitary mixing for the non-unitary mixing case. Yeah. I mean if it is show up in the first two row, if then nu E and nu mu are the good probe, but if it shows up, exactly. So for the third row, to test the third unitary property of the third row, we knew the nu mu to nu tau oscillation probability. Have been tested in other experiments with nu mu and nu E. Yeah. That's the reason oh, okay. Yeah. So yeah, so because the original plan of DUNE is to observe the muon on electron. So tau neutrino is an additional handle. So it will observe muon and electron here. Yeah. We would like to constrain it more. And that's why we need the tau neutrino. Yeah. So now the challenges for determination of tau neutrino at the long baseline experiments. So when we detect the neutrino flavors, we detect their corresponding charged lepton, right? So when we say that we are detecting nu E, we are basically observing electron in the detector, or when we are detecting nu mu, we are observing muon at the detector. And the neutrino flavors go through the charge current interaction at the detector and then produce the corresponding charged lepton. So for nu tau to produce the tau neutrino, the threshold of the charge current interaction is 3.5 GeV. And the previous neutrino experiments, so the currently ongoing experiments, NOVA and T2K, their neutrino beam is below that 3.5 GeV energy, and so that's why they cannot determine tau neutrino at the detector. And also another thing is that the tau neutrino has a very short lifetime, so we need a very good spatial resolution at the detector to determine the tau neutrino, and NOVA and T2K do not have that also. So DUNE will provide us this to help us in these two aspects, that it will have an energy beam above 3.5 GeV, and also it will have a very good spatial resolution for the detector. Now
detect tau neutrino is to see like displace something, is it, with a displace vortex?
Yeah.
Because of missing neutrinos or what? I mean, yeah, because otherwise we could do invariant mass, right? Which we cannot do.
Yeah. So
or I can look at some number of tracks and some bending, stuff like that.
Yeah.
But none of that is possible in a neutrino detector, and we have to see the displaced vortex. That's the point, right? So I can look for characteristic signals, which I could do. Then the spatial resolution is not the only way to do it. Yeah. No, it is said as requires very high spatial resolution, but that's one way to do it. I'm saying it's just not
Okay,
requires.
yeah.
Yeah,
That's
all right,
yeah. It's not the For DUNE it's an additional opportunity, but yeah, it's not the only one.
No, if you had put best way to look at work,
Yeah.
you said requires, so you.
Yeah. The wordings are not probably very correct. So
the DUNE beam.
yeah, I'm showing it in the next slide. Yeah. So DUNE has two kind of beam. One is the regular DUNE beam, so which is this one, and one is the high energy beam optimized specially for tau neutrino detection, which is this one. So we can see that the regular beam peaks below 3.5 GeV, but it's not very low at 3.5 GeV also. And the tau optimized high energy beam, it peaks at exactly 3.5 GeV. And by new and old, by old I mean the flux used in previous studies like these two papers, and they are available in this DUNE collaboration paper. And by new I mean the flux we have used in our work, and we have taken the flux from this collaboration paper and also from this website. So I hope that answers your question. The energy of the DUNE beam.
Flux is the one they're going to use, or
Yeah.
Okay.
They so they have upgraded their flux. Yeah. So now the non-standard interactions. Okay. So in the Lagrangian level, we write the non-standard interaction by a dimension 6 operator. So this F are the fermions in matter, that is electron up quark and down quark, and alpha and beta denotes the neutrino flavors, electron, muon, tau. So what I want to give importance to is that here we allow flavor changing neutral current interactions as well. So my alpha and beta may not be same. And when there are flavor conserving interactions, so that means when alpha and beta are same, the coupling constant is different than the Fermi constant. So and then at the Hamiltonian level, it adds up as an additional matter potential with non-zero off-diagonal term. So this is the vacuum neutrino evolution Hamiltonian in vacuum written in the interaction basis. So M1, M2, M3 I have already defined that they are the mass eigenvalues for the mass eigenstates, and then this H matter is the is the potential energy gained by the neutrino because of the forward scattering through matter. And then we have this additional non-standard interaction term where we can have the non-zero off-diagonal terms, allowing me to have the flavor changing interaction possible. So the diagonal terms are real numbers and the off-diagonal terms are complex numbers. So there will be additional phases involved with these off-diagonal terms.
That PC is a 3x3 matrix. Is it? F is like full all three flavors? Or
yes.
What?
No. F is EU
right.
and D. Yeah.
Oh, EU and D.
Yeah, because in the matter you will have electron, proton, and neutron. So the fermions will be electron, up quark, and down quark.
But same, is it? F bar F.
Yes.
F and the two Fs are the same.
Yes. So we are not allowing flavor changing neutral current
Why?
in the charged lepton. We are allowing them only in the neutrinos.
Yeah. Why is that?
Because we are
Like I could have U bar D here and then nu bar E or something. I could do that, right?
uh, um, mm, I guess the we have not seen flavor flavor change in the charged lepton. We have only seen flavor change in the neutral leptons through neutrino oscillation. So we are allowing only the flavor.
No. But charge current is flavor changing, right? I mean, it's
Charge.
like,
This is neutral current first of all.
so all the more reason to first do charge current because we have
Okay.
actually seen flavor change in
Yeah,
charge current, but loop is like neutral current is only loop level.
Yeah, so the charge current NSI is constant at the near detector because we see the neutrinos through charge current interaction. So if there is any charge current interaction, that will be observable in the detector, and we have the near detector at the experiment. So the near detector will constant the charge current in any charge current NSI. So when we consider the neutral current NSI, when we consider the NSI during the propagation of neutrino through matter, we are considering the neutral current NSI.
I see. Okay.
So now if we want to write the oscillation probability for muon neutrino to tau neutrino considering NSI, then for three flavor oscillation, we can treat the NSI as the perturbative term and we can write up to second order. So this paper gives the detailed calculation of the oscillation probability for oscillation probability considering NSI for all different oscillation probability. So it gives the oscillation probability for muon neutrino to electron neutrino, tau neutrino, from tau neutrino to muon neutrino, electron neutrino, every kind of oscillation probability considering NSI. So from this paper we found out that we can write the muon neutrino to tau neutrino oscillation probability considering NSI like this, where this term is the vacuum oscillation probability in two flavor model, and it is given by this expression. So this 4 cos square theta 2 3 sin square theta 2 3 is basically sin square 2 theta 2 3. So that means that it is not sensitive to octant of theta 2 3, and because of sin square delta 3 1 L over 4E, this is not sensitive to the sine of delta 3 1 as well. Now if we consider this this term, then the contribution from epsilon mu tau can be written like this. So we can see that because of the sin square theta 2 theta 2 3, it is not sensitive to octant, but because of sine delta 3 1 L over 2E, it is sensitive to hierarchy. Now if we consider the value of this mod of epsilon mu tau equals to 0.2, and if we put phi mu tau equals to 0, then this term becomes 10 times larger than the other subleading term, and that's why there will be significant contribution of epsilon mu tau in the neutrino oscillation probability from nu mu to nu tau. Phi mu tau is the phase associated with epsilon mu tau. Epsilon mu tau is a complex term, so we can write it as mod of epsilon mu tau e to the power I phi mu tau.
Sorry, the propagation is sensitive to the phase, right?
Yes, the oscillation probability.
Then why are you putting it to 0?
No. It is just to show. It is just to a toy model to show that.
But there is sensitivity to.
Yes. I will show that later. It is.
And you can disentangle this epsilon mu tau, the modulus and the phase.
Yes.
By looking at the observables, you can disentangle them.
Yes. Yeah. So that is what I am going to show.
Okay.
Yeah.
Okay.
So now epsilon mu and epsilon tau, the contribution from these two diagonal term is proportional to cos square 2 theta 2 3, and since theta 2 3 is close to pi by 4, so cos square 2 theta 2 3 is close to 0. So that means their contribution will be very small. And also the contribution from the other two non-diagonal term epsilon e mu and epsilon e tau, that always comes in the second order. So they are so they are also negligible. Now for this work we have considered these 5 possible runs at DUNE. So the first one is we will consider muon neutrino survival probability and electron neutrino appearance probability after 5 years of neutrino and 5 years of antineutrino run with regular beam. And then we will consider muon neutrino survivable and tau neutrino appearance probability after 5 years of neutrino and antineutrino run with regular beam. And we will consider all these two. We will consider both of these cases in this run. So we'll consider muon neutrino disappearance, electron neutrino appearance, tau neutrino appearance after 5 years of neutrino and antineutrino run with regular beam. And then we will have the same like this, but we will have additional 1 year of neutrino and antineutrino run from the tau optimized high energy beam. And here this is same as this, but we will again consider 1 year of neutrino and additional neutrino and antineutrino run with the tau optimized high energy beam. And this is the proton on target for both regular and high energy beam per year.
Sorry, I'm a bit confused. If I look at the first two rows, what does it mean? So if I run for 10 years, I
5
can
years of neutrino and 5 years of antineutrino in the beam.
But why does it say mu plus E and mu plus
Oh,
tau?
because we will observe the muon we will consider the muon neutrino and electron neutrino.
But
at
I
the
could also
data.
look at the tau neutrino.
Yeah.
Right?
So that
Why do we split it up? I mean, I
Because-
can look at all three.
Yeah, so this is coming here. I'm
Yeah.
splitting it up because the original plan of DUNE is so DUNE can do all its physics goals with just this, right? And
Oh.
I am trying to see what additional thing we can get
I
from
see.
tau neutrino detection.
Okay.
Yeah.
But nothing is changed in the beam or anything.
No.
Okay.
Yeah. So this is the event rates of, so this is new tau plus new tau bar event rates after 5 years of neutrino and 5 years of antineutrino run with regular beam. And the ellipses come from varying delta Cp in the range minus pi to pi. So if we look at that, we can see that epsilon mu tau has have a very different event numbers from the standard thing, but for other new NSI parameters, they are not distinguishable from the standard interaction case. And also we can see that the event rates for normal hierarchy and inverted hierarchy in case of epsilon mu tau are very different. So there should be hierarchy sensitivity at the tau neutrino appearance channel for epsilon mu tau.
Sorry, I don't see. Where is the red there?
Yeah, here.
That tiny thing, is it?
Yeah. So that means that tau neutrino appearance does not have any CP sensitivity because this is delta Cp. This is delta Cp plus 90 and this is delta Cp minus 90, and there is you cannot see, you can just see a straight line. So that means that your Cp violation change in the value of delta Cp does not have any effect on the new tau appearance probability in the standard.
Sorry, the lines are when you change delta Cp, is it?
Between minus pi to pi. Yeah.
Okay, that's why you get
Yeah, that's why we have the ellipse.
So the difference is about like 10 events or something.
Between what?
Within that ellipse, like order of 10 or
Yes.
Yeah.
In between this, yeah. So I mean, not very large. I mean,
and what determines how big you make these epsilons? Like can you take them even bigger or
no, they're constant from
They are
other
constrained?
experiments. Yeah, they're constant from other
this
experiments.
is the maximum allowed? Or?
No, I think you can have more. But if NOVA and T2K best fit, if you analyze the NOVA and T2K data, that gives a best fit of epsilon E mu and epsilon E tau to be 0.2. So I wanted to be consistent with that result.
Best fit meaning limit or
No, so
It
NOVA
gives
and
you
T2K,
0.2.
NOVA and T2K has a small tension at 1 sigma level.
I see.
So if you analyze that data, that tension can be resolved, and then you get a best fit of epsilon E mu and epsilon E tau close to 0.2. So
I
it's
see.
around 0.16 or so, but close to 0.2. So I want to be consistent with that result, and that's why I kept everything at 0.2.
What significance is that result? How many sigma is it?
I think at 1 sigma, it's a
Oh, I
very
see.
small tension.
Okay.
Yeah. But still, it's a best fit point. I mean, they choose it as a best fit, and I think epsilon mu tau 0.2 is not allowed at 90% confidence level. It is allowed at 3 sigma, 3 sigma limit. Yeah.
So you have done it at the 90%, whatever is allowed, you have taken it there.
I would say I have constrained myself in the 3 sigma allowed, not exactly 90, because epsilon mu tau 0.2 is not allowed at 90%. It's allowed at 3 sigma.
Okay.
Okay, this is the nu plus nu bar event rates, again by varying delta Cp from minus pi to pi, and we can see that for epsilon e mu and for epsilon e tau, we can see that the ellipses are larger, so that means they have good delta Cp sensitivity for these two parameters with nu appearance probability. But epsilon e mu and epsilon e tau are not well distinguishable from each other. Okay, now how I will talk about phi mu tau hierarchy degeneracy. So we saw that the contribution from epsilon mu tau looks like this, and because of this sine delta 3-1 term, there is a hierarchy sensitivity. But the thing is that if we consider normal hierarchy and phi mu tau 0, that oscillation, then it can be mixed by inverted hierarchy and phi mu tau equals to pi. So that means there is a hierarchy phi mu tau degeneracy, which will reduce the hierarchy sensitivity for epsilon mu tau also in the nu tau appearance channels. And here is a demonstration of the degeneracy. So we can see that normal hierarchy and phi mu tau 0 can be mimicked by inverted hierarchy and phi mu tau minus 180 degree and 180 degree, and similarly normal hierarchy and phi mu tau 60 degree can be mimicked by inverted hierarchy and phi mu tau 120 degree. So because of this degeneracy, we will not get hierarchy sensitivity for epsilon mu tau also in the tau neutrino appearance channel. Okay, so this is the mass hierarchy sensitivity. So this is for the standard case. We can see that with standard case, with electron neutrino appearance, NOVA has a very definitive, DUNE will have a very definitive hierarchy determination probability, and tau neutrino appearance does not have any hierarchy determination capacity as we saw before. And with epsilon mu tau, the hierarchy sensitivity of DUNE for electron neutrino channel also diminishes a bit, but still it has a good hierarchy. It will have a good hierarchy sensitivity, and of course tau neutrino does not have any hierarchy sensitivity because of the pi mu tau hierarchy degeneracy.
Sorry, why is it that tau does not have good sensitivity? I mean, why does tau? So if you look for epsilon mu tau, you would have thought that tau appearance would have the best sensitivity, no? Then why is it that electron has the best sensitivity?
No, this is for the hierarchy. This is for the hierarchy determination.
I see.
Not for the sensitivity of epsilon mu tau. I will come there also. Okay, this is for delta Cp and octane sensitivity. This is for the standard case, and I have some backup slides to show the NSI cases also. But as we can see that the delta Cp and the octane sensitivity are based with the electron appearance channels for standard case, and the same goes for NSI also. If you are interested, I will show the backup slides later. This is the sensitivity to epsilon mu tau as you were asking. So we have considered the true event rates with standard case. So we have considered that in nature there is no NSI. So then can we constrain epsilon mu tau in the DUNE experiment? That was the question. So we can see that the best sensitivity comes with the tau neutrino by the addition of tau neutrino appearance channels. For epsilon mu mu and epsilon tau tau also, addition of tau neutrino have a competitive sensitivity compared to electron neutrino appearance, and that is because for these two parameters the sensitivity mostly comes from the muon channel. So addition of electron and tau neutrino does not contribute much. So basically with mu plus e or mu plus tau or mu plus e plus tau, we have very close sensitivity.
Sorry, where it was saying that tau will add a lot. Sorry, for let's say 95% exclusion, what delta chi square should I take?
If for one sigma, so the square root of delta chi square is the sigma. So this is 20 sigma, this is 40 sigma. So this is yeah. And if you want the limit, This is for the plot, but I have a table also with the with the limits. I'm going there now. Now the thing is that we saw that because of this cos phi mu tau terms, there is this hierarchy phi mu tau degeneracy. But also, if we know the hierarchy very determinedly, then tau neutrino can help us determine phi mu tau. So here the question I am asking is that if the NSI phase in nature is 0, can DUNE precisely measure it? And here we can see that the best precision measurement come after addition of tau neutrino appearance channel for phi mu tau, because of the presence of that cos phi mu tau term. Yeah, but I mean, it's a bit better. Marginally better. Yeah. Yeah, this is phi mu tau. Yeah, so this is phi mu tau. This is minus 180 minus.
Chi-square is plus 5, can you read the limits?
Yeah, this is minus 60 and this is plus 60.
Forward it. Right?
Yeah, but this is not chi-square phi. This is 5 sigma. This is square root of delta chi-square. No, you don't know to go beyond that. Yeah. Yes. So here, but for 5 sigma, I guess tau neutrino addition of tau neutrino comes to 5 sigma closer to 60 degree. I mean, yeah. It's so, but for other NSI phases, tau neutrino does not have much effect. And here is the constraint. There is the 90% constraint on tau neutrino, 90% and 3 sigma limits on different NSI parameters after for these different beam runs. And as I said that with epsilon for epsilon mu tau, tau neutrino has a competitive sensitivity as electron neutrino channel, and for mu and tau also, because as I said that the sensitivity for mu and tau mostly come from muon disappearance, so the appearance channel do not change that much. But for the other two parameters, epsilon mu and epsilon e tau, electron neutrino appearance have much better much stronger constraint than tau neutrino appearance.
Sorry, can I repeat my earlier question? So even if I add tau, epsilon mu tau is not helping that much, right?
No, it's not helping. Because of the event number. Look at the event numbers. So here we're talking about 220, 60, 160, 75, right after 5 years of neutrino and anti-neutrino run, and look at the event numbers here. They're 10 times larger than the tau neutrino appearance event.
Well, the flux said that energy is small.
Yes, and also the cross section is yeah. Also the cross section.
Both of them.
So for the 5 years, for 5 years, the flux is small at that level. But I have also checked with the high energy beam for 1 year and 1 year. It's just one. I mean, I have just considered the 1 year run there. So the what 5 year regular beam time produces, the 1 year high energy beam produces the similar number of events. Yeah.
So uncertainty will only be uncertainty in that number, but it won't explain why the number itself is small.
Right? No, yeah, exactly.
Saying that it's a small number is uncertain.
Yeah, uncertainty will reduce the delta chi-square even more. Yeah.
Here we are asking why is the number.
Yeah, the number is more small for the cross sections, and also the secondary reason is the flux, because the flux is also small. Okay, yeah, I'm almost done. So this is done. Then I'm taking a small detour for this testing the unitary property of the third row of the PMNS matrix. So the non-unitary will arise when there will be sterile neutrino which will be very heavy at the TeV scale. So there will be and they can be treated as isosynchrate neutral heavy lepton. So for this case, these heavy neutral leptons will not take part in the neutrino oscillation, so we cannot observe them in the direct sterile neutrino surge. At the same time, They will not take part in the weak interaction, but they will make the effective three flavor mixing matrix non-unitary. So there is a catch here that in this case they can be very strongly constrained from the charge lepton flavor violation experiments. So then if we want to have large non-unitary mixing in the neutrino oscillation without violating the charge lepton flavor violation constraints, then we need to have light sterile neutrinos with mass in the range of 100 electron volt. In that case, the sign delta 4 L over 4E, if this becomes around 100 electron volt square, then this goes through very fast oscillation and it can be averaged out. So we will not be able to observe the sterile neutrino in the direct neutrino search. But when we will write the charge lepton flavor violation terms, we have to consider the effective 4x4 unitary matrix. So we cannot constrain non-unitary parameters from CLFB experiment, and the effective 3x3 Hamiltonian effective 3x3 mixing matrix will be non-unitary. And in that case, we can have large non-unitary mixing in the neutrino oscillation experiment without violating the strong constraint from CLFB experiment. And then the non-unitary mixing matrix effective in the effective three flavor region can be written like this. Here I have made a mistake. There will be this U matrix there. U is the PMNS matrix, and this NNP will be denoted by this matrix. So then after that, so these are so as I have said that they are constant from the charge lepton flavor violation experiments, and these are the constant on the third row elements of the non-unitary parameters. So these are the 3 sigma limit, and the outside limits are from the joint fit of neutrino oscillation data and charge lepton flavor violation experiment, and inside the parenthesis I am showing the limits from only neutrino oscillation data. And then in the DUNE experiment, if we consider tau neutrino, we can see that the addition of tau neutrino will have the best sensitivity to these non-unitary parameters. And in fact, for alpha 22, the DUNE tau neutrino detection will give us better fit than the present limit on the alpha 22 parameter.
Sorry, you're talking about improving the previous one. Like
yes.
Already a very tight.
Yes. Yes.
So this will improve.
This will improve. I have to check that. So alpha 22 was a point for only neutrino oscillation data. It was 0.76.
Like 0.76.
Alpha 22 must be greater than 0.76 for only neutrino oscillation data.
So what is that 0.99?
That is addition of CLFB data with only neutrino oscillation data.
But we would like to add it.
Depends, as I said, that if we have the neutral heavy lepton at the TeV scale, then CLFB can constrain it. But if we have a light sterile neutrino of around 100 electron volt mass, then CLFB will not be able to constrain it. In that case, neutrino oscillation will constrain that range also. For the neutral heavy lepton of around TeV scale.
The neutral heavy electron is a sterile neutrino?
Yeah, sterile neutrino. Yeah.
But if it is T, then 0.99.
Yes. 0.9. Then the only neutrino oscillation data will be better. Yeah. So and it will improve that.
How much? 0.76 will get improved.
Yeah, 0.76 at 3 sigma, right? So this is 3 sigma. So you can see that it goes above 0.8.
By a whole.
Not by a whole lot, but if you add that with the other data, then you can have a lot of improvement. So
this alone will do 0.8.
yeah, this alone, the DUNE alone will do 0.8, but if you add it with other neutrino oscillation data, it will improve even more. Okay, so we consider so the conclusion is that we consider the impact of this new tau detection at DUNE in relation to NSI. So the most significant contribution to tau events is from epsilon mu tau, in which mu tau will boost the sensitivity by a tiny bit. But if mass hierarchy is fixed, then mu tau will help in determining the phase phi mu tau. So strategically, one can measure mass hierarchy from new appearance data and then add nu tau appearance and nu appearance together to have a better precision measurement of phi mu tau. And for the standard oscillation parameter, nu tau detection will not have any effect. So tau appearance channels will only provide the complementary constraint on NSI parameter and BSM physics. And I have not mentioned it here. I have already shown that for non-unitary constraining the unitary violation, tau neutrino can be helpful at DUNE. Thank you. And yeah, so there are some backup slides I can discuss with you later. But this is one I think I want to mention, that there is a relationship between this epsilon alpha beta at the Lagrangian and this epsilon at the Hamiltonian. So this is the relation. So this NF is the number density for the fermions, and Ne is the number density for the electron inside the core of inside the earth matter. And since we consider a neutral isoscalar earth matter, so we can consider that NP and Ne are equal, and then the number of neutron are almost equal to number of protons, and then the relationship between this alpha and so this epsilon and this epsilon becomes like this.
Any more questions?
I just had one. So I was just wondering, it looks to me like adding neutrino appearance didn't do a whole lot. Am I getting this wrong, or?
Tau neutrino appearance.
Yeah.
Yes. It did not. It does not do a whole lot.
Which is very surprising. No, you would have thought that if you look at tau
It's
appearance.
not surprising if you look at the oscillation probability. It's not surprising if you look at the oscillation probability, and if you consider that the tau neutrino have very low cross section and very low cross section, so the event numbers
as you mentioned,
get
that is
reduced.
the main reason. The cross section is small.
So event numbers get reduced.
Theta 2-3 actually provides the mu oscillation, and that is maximum. So when your mu goes to 0, it's 100% going into tau, because that theta 1-3 is very small. So there's a huge generation of tau because of this, and that happens at higher energy around 15-16 GeV. But if you see that, then you're actually confirming oscillations itself, which has been confirmed indirectly by slow everything. You actually see this production of mu tau. Mu tau is huge, see, but mu tau interacting and producing charged tau is very small.
So, I don't know if you would agree with the statement that, because we have unitarity, regeneration unitarity, we have looked at other things, more or less everything is constrained. And just adding just tau appearance is not doing a whole lot. But if I now give up unitarity, it should have then added a lot, but somehow it didn't. And that part is puzzling. Because the cross section is small.
Because the event numbers are very small.
Or now if we go to heavier or higher energies, if we can produce a beam of higher energy, then we should see a lot of it.
But producing a 15 GeV beam is a...
This is not practical, but I'm just saying.
No, but...
Because of flux.
It's flux up to PV.
In fact, this PV event rate that Chemtranet has observed, that's a new tau. That's a new tau event, right? Yeah.
They've seen this.
PV level neutrino. I guess only one.
Like DUNE is shielded from all that, or what?
No, DUNE atmospheric.
But it's not. You should be able to tell charge apart, or what?
see the atmospheric neutrinos.
Yeah.
That they will do separate.
Yeah.
Ah.
What you cannot-
So there you should see a lot of
Yeah,
sensitivity to
the atmospheric
tau appearance, right?
the atmospheric and also the astrophysical neutrino group will see it, and in fact the atmospheric neutrino group in the DUNE are the people who are most interested in the tau neutrino detection. Yeah.
Sorry, a naive question maybe. Are there any proposals to use collider neutrinos? Like phasor, I know, is something which is using these collider neutrinos, but probably that is not the correct baseline for observing oscillations. So are there any experimental proposals which people are thinking of which can, because collider neutrinos can have anything from GeV to TeV, so that will not be a problem for generation. So are there any such experimental proposals?
Opera was an experiment with collider neutrino, right? Right? Yeah.
It will be large. That's not,
Oh, okay.
even for, I mean, you can have tau neutron. I'm not sure if they measure tau neutron.
100,000 of what from
No, okay. Okay. But
Okay, but collider systems will also have pion background. Okay, that's not something I'm familiar
this
with.
formula. Yeah.
Okay.
I think
The hall is same. Yeah, yeah.
That is why they have learned to pollinate much better. Any collider will not be able to pollinate your.
okay. If you don't have any more questions, we will end here. Thank you. Thanks a lot.
Thank you.